Well, hello. Today what we're going to do is go through some weak acid calculations. I want to review with just the general calculations for acid bases and the equations we used. So this should look familiar. I'll leave this up for a few seconds in case you need to pause to write any of this out. This is how we went from pH to H3O+. We went through this in a previous presentation, and this allows you to go anywhere from pH to POH to hydroxide to hydronium concentration, and this works very well for all strong acids. Today what we're going to discuss is weak acids, and it's a little bit different. If you remember, strong acids dissociate fully, so we have our acid, our proton and the anion in water. It's a single one-way arrow, and it goes into the hydronium ion plus an anion. So in water, this donated a proton. That's why it is an acid. And oftentimes we just write HA goes to H plus and A minus. We know that the HA concentration is the same as the H plus concentration. If it's a monoprotic acid, those will be the same concentration. In other words, if this is 2 molar, then the acid in solution will be 2 molar. We had discussed Kw earlier, and I'm simply going to click through these just to expose the slide, and then we'll get into the discussion today. So Kw, remember, is always equal to H3O plus hydronium times hydroxide. Numerically, Kw, the water dissociation constant, has a value of 1 times 10 to the negative 14th. So if you know the hydronium concentration, you can easily get the hydroxide. If you know the hydroxide concentration, you can get the hydronium by simply taking 1 times 10 to the negative 14th divided by whichever you have. I'm going to represent hydronium this way. The little red dots represent the hydrogens, so H3O with a 1 plus charge is equal to 1 times 10 to the negative 14th divided by OH, just applying this equation at the bottom. If we wanted to get the OH concentration, it's going to be 1 times 10 to the negative 14th divided by hydronium equals hydroxide. So that's how we can go between hydronium and hydroxide for a strong acid. We had discussed the pH scale, mentioning that it ranges from approximately 0 to 14. The 0 would be in the numbers less than 7, acid, greater than 7, a base. And we can get pH. pH is always equal to the opposite log of H plus or H3O plus. If you know the pH and you're trying to get the H plus, you take the anti-log or 10 to the negative pH power to get the concentration of the H3O plus. That's how we can go between these two. Now we want to start talking about weak acids. We know weak acids are reversible. They don't break down 100%. So that's what the double arrow indicates. So I've got my weak acid in water, donates a proton and an anion, but sometimes the hydronium ion gives back to the anion its proton, and it reverts to the original portion. So how do we represent, how do we figure out what the pH is going to be? Well, that's going to be a whole new set of calculations we need to master. So in order to do this, we're going to need to utilize the acid dissociation constant designated K sub A. It's a type of equilibrium expression, and it's always equal to the concentration of the products divided by reactants. And for my equation here, the products here are H3O plus and A minus. So I put H3O plus and A minus on the top. The order doesn't matter. Divided by the reactants, the concentration of the HA. Water is never included in a Ka expression. So this slide will be very important to you as you get ready for the test to kind of review and summarize some of the equations. So let's get started now on our calculations for today. So as I mentioned earlier, Kw is the water dissociation constant. It's always equal to H3O plus times OH minus. Now in regular distilled water, freshly distilled water, the concentration of H3O plus and OH minus are exactly the same. They're both 1 times 10 to the negative 7th. If you were to take the opposite log of 1 times 10 to the negative 7th, you get a pH of 7, which is why freshly distilled water has a pH of 7. If you took 1 times 10 to the negative 7th times 1 times 10 to the negative 7th molar, because I said they're the same concentration, you will get the numerical value of Kw, the water dissociation constant, and it will be 1 times 10 to the negative 14th. That's what I showed you on the previous slide, how we convert between hydronium and hydroxide is using this equation. Now, there are other equilibrium expressions besides Kw. There is an equilibrium expression for an acid and for a base and for water. They're all written in the same fashion, products over reactants, because these are all reversible type reactions. So this one is specifically for water, this is for a weak acid, and this is for a weak base. So let's look at this example here. Does this represent a strong or weak acid? Well, strong the way I've written it, because there's a one-way arrow. And so that's what we mean with the one-way arrow. So this second one must be a weak acid, because I see it's a reversible reaction. Now let's do a little bit of thinking about these equations. Let's look at this one here. The way I've had this written, it indicates it's strong, but ammonium ion is a weak base. So ammonia is a weak base, so we need to make it reversible. Now, there's some terms we want to learn, and there'll be another presentation for you to watch about conjugate acid bases. But here we have the ammonium ion, NH4 1+. And what you can see is it's donated a proton, and what's left over is the ammonia molecule. Whatever you start with after it donates a proton is called its conjugate base. That's what CB refers to here. This is its acid, this is its conjugate base. Now, because this is reversible, what I can do is reverse it. Now notice that I have this is the H plus is acting as an acid. Whatever accepts an acid would be considered a base. And then whatever it turns into would be called its conjugate acid. So there's some terms that we'll need to practice identifying a conjugate acid or conjugate base, and I'll have another presentation that will go through that in much more detail for you. Okay, so let's look down here now with a strong acid. If I start with a strong acid of 0.1 molar, then the proton concentration will also be 0.1 molar, and the anion concentration would be 0.1 molar. We're simply using coefficients. If there's a 1 in front of the HA, a 1 in front of the H plus, a 1 in front of the A minus, they will all be 0.1 molar based on the original concentration. If I wanted to calculate the pH, I would use this value right here, the 0.1 molar of the hydrogen ion. And we've done that calculation as well before. If we have a weak acid that's 0.1 molar, we might assume that the H plus is 0.1 molar, but in fact, it's not 0.1 molar. Is it going to be more or less, do you think? It'll be less because it doesn't donate all of its protons. So we need to figure out what is that concentration. Now, I've put a statement here about relative strength of conjugate acids and bases. If something is a relatively strong acid, its conjugate base will be very weak. If something's a very weak acid, its conjugate will be very strong. This concept will be much more important for you if you move on in chemistry. For our first year study of chemistry, and the fact that we're having very shortened class periods, I'm not going to spend a lot of time on this slide, so I'm just going to continue through our discussion. We're not going to be discussing the leveling effect to any great extent, so I'm also going to skip through this slide as well. You're welcome to read it if you wish, but hit pause because I will continue here very quickly. All right, so let's get into some weak acids. I'm going to define a weak acid as one that dissociates incompletely, let's say 20% or less. A strong acid, we're going to say, dissociates completely, about 100%. Now, I know there's stuff in the middle. Those would be strong weak acids or stronger weak acids. There are only 7 strong acids. I'm not going to make you memorize those. Now, let's learn to write an equilibrium expression. So these all have to do with gases. We'll pretend this is a balanced chemical equation with coefficients. If it is a reversible reaction, it would need a double arrow, so we'll put that in there. Now, anytime you write an equilibrium expression is always equal to the concentration of products divided by reactants. So if I wanted to write an equilibrium expression for this equation, it would be equal to the concentration of C times the concentration of D, those are my products, divided by the concentration of A and B. Now, to finish this, I need to pay attention to the coefficients. The fact that there's a coefficient 3 in front of the C, I'm going to need to cube the concentration. So if C was 2 molar, 2 cubed would be 8. So I would have to cube that. So what do I have to do with the B? If you notice there's a 2 here, that means I have to square the concentration of B. So if it was 2 molar, it would end up being a 4 numerically in my equation. This is the way we'll write a KEQ expression. Most of these you will have tabulated data that you can look up, and the important part for us is understanding what the magnitude of the number means. If KEQ is a large number, that means you'll have a lot of product, very little reactants. It means a large KEQ favors the product. A small numeric KEQ value means that it favors the reactants, or very little of it will dissociate. Again, this is described by Le Chatelier's principle about stressing a system. You can review Le Chatelier's if necessary. Okay, let's go through and try an example now. You might not recognize this. This molecule here is C2H3O2H. We call that acetic acid. Sometimes we write it this way, sometimes we write it this way. It looks like kachoo. This part right here, the COOH, is a C double bonded to an O with an OH. That's called a carboxylic acid. That's a very important functional group as you move on in chemistry. For us right now, it's not important to know. What is important to know is that acetic acid is a weak acid, so it will donate a proton. Now, you've got a hydrogen here, 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 and down here. It's actually going to remove this hydrogen ion, and that's due to the fact that you have an oxygen here and an oxygen here. They're both highly electronegative, and they're going to pull electrons toward them away from the bond between the oxygen and the hydrogen, weakening it, and what happens is that hydrogen on the end drops off. So it donates a proton, and we're left with the acetate ion. Now, this is a reversible reaction indicated by the double arrows. Most of the time, the acetic acid will hold on to its proton. Every once in a while, it'll donate a proton. So we want to figure out what this means to pH and how we can figure that out. So we could write an equilibrium expression for this equation, and it would be equal to, as we stated earlier, the product concentration divided by the reactants. So for us, the products are H plus and acetate, and the reactant is the concentration of the initial acetic acid. Now, because this is an acid, the equilibrium expression for this is called its Ka value, acid dissociation. Numerically, it's exactly the same, except because it's for an acid, we give it the subclass acid dissociation constant. Now, we can look up in a textbook or a reference the Ka value for acetic acid, and here it is. The acid dissociation for acetic acid is 1.8 times 10 to the negative fifth. That's a unitless number. And that's at room temperature, about 25 degrees Celsius. So what can we do with this? Well, we're going to try to figure out what the H plus concentration is, and therefore figure out the pH using the Ka value. So if you remember the problem before, we said that the acetic acid was 0.1 molar. Now I've substituted in for my Ka 0.1 molar. So we're going to put that into the equation. Now at this point, I can't quite solve this because I have two unknowns. But let's think for a second. When acetic acid breaks down, it makes one proton and one acetate ion. These will always be in the same ratio and the same concentration because they're coming from the same substance. I don't know this, it's X. I don't know this, it's X. I can do this because they're going to be the same concentration. So now I've changed my expression to say 1.8 times 10 to the negative fifth equals X squared divided by 0.1 molar. I can easily do the algebra on that, multiply these together, equal X squared, and then finally take the square root. When I do that, X comes out to be 1.34 times 10 to the negative third molarity. What does that represent? Well, it represents both the concentration of the acetate that I'm not truly interested in and the hydrogen ion concentration that I do want. Now, our original question was trying to figure out what is the pH. Well, now I can get there because now I have the hydrogen ion concentration. If you recall, pH is equal to opposite log of H plus. So I'm not going to put in 0.1 molar for H plus. I'm going to put in 0.00134 or 1.34 times 10 to the negative third molar. When I type that in my calculator, I realize that the pH of my solution is 2.87. And this is how you calculate the pH of a weak acid. You must utilize the Ka expression. I hope that makes some sense. We'll do a couple more examples to flesh this out for you and make this make more sense. Before we do that, I want to give you some values of acids. Here's a strong acid, HCl. It has a very large Ka. A very large Ka would be close to 1. 1 would be considered a very strong or 100% dissociation. Nitric acid, another strong acid, very large. Sulfuric acid has a large Ka. It's not quite as large, but it gives most of its protons away. Here's acetic acid, clearly a weak acid, and there's its Ka. And here's a very, very weak acid, H2S. It's 9.5 times 10 to the negative 8th. In fact, we wouldn't really consider this a weak acid. We would consider this more of a base, because if you remember, the stronger the weak acid, the weaker its base. The weaker its base, the stronger its acid. So this would be really a base more than an acid. But I just put it in here to show you that we can come up with Ka values for lots of different substances. Nothing new on this slide. On the top, this is the table we were looking at earlier. Again, just more values. I'm not going to ask you to know these. I'm just showing you that they're readily available, easy to look up. The stronger the acid, the higher the number. All right, now let's do a problem. So these are going to look a little scary at first because they have words and not just math, but we're going to work on these together, and I think it'll make a lot of sense to you. So we're going to start off with 1 gram of concentrated sulfuric acid, and we're going to dilute that into 1 liter of water. And I want to know what is the molar concentration of the hydrogen ion, as well as what is the pH that will be produced. Now, this is not a typical problem, but I just kind of want to go through some math with you to keep you fresh. So here's what we're going to do. We're going to first determine how many moles we have. So we have 1 gram of sulfuric acid, and therefore I must need to figure out its molar mass. So in order to do that, I have 2 hydrogens, each that weigh 1 gram. 2 times 1 is 2. Sulfur weighs 32 grams per mole, and 4 oxygens times 16 is 64 grams. So that means that I have 1 mole of sulfuric acid is 98 grams. That's the molar mass of sulfuric acid. Grams of sulfuric acid cancel like that, and I'm left with moles of sulfuric acid. Okay? Now, how do we go from moles to molarity? Well, if you remember that, we're going to have to use our equation. Molarity is moles divided by liters. Now, this is important because we're interested in the ion concentration. Initially, we have a 0.01 moles of sulfuric acid. Let me just digress for just a moment. Sulfuric acid donates a proton, and you're left with this HSO4 minus ion. A split second later, that HSO4 minus donates a second proton. Generally, we don't write it in 2 separate steps. We just write it in 1 step. And we would write H2SO4 goes to 2 protons and an SO4 2 minus. And in a dilute concentration of sulfuric acid, which 0.01 moles in a liter would be considered dilute, it's basically going to occur 100% of the time. So I didn't show you this, but if you took 0.01 moles divided by 1 liter, that would give you 0.01 molar sulfuric acid. So again, I went from moles to molarity by using the equation molarity, big M, equals moles divided by liters. Now, if the sulfuric acid is 0.01 molar, and there's a coefficient 2 here, the hydrogen ion must be double that, or 0.02 molar. The sulfate ion, because there's a coefficient 1 here and a 1 here, is 0.01 molar. I don't need that value. Now, we were trying to answer a few questions here. The first one was, what is the molar concentration of the hydrogen ion? Well, there's the molar concentration of the hydrogen ion, 0.02 molar. And the second part says, what is its pH? Well, to get the pH, it's opposite log of H+. So I'm going to put in, for H+, my 0.02 molar. Type that into my calculator, and I get a pH of 1.69. This is a strong acid in water, and you can see that's a relatively low pH. Now I'm going to do a similar type calculation, again with a weak acid, acetic acid, to show you how that calculation looks a little bit different. So now we're going to start with a volume of 5.71 cubic milliliters of pure acetic acid and dilute it in water in 1 liter of water. Now, I've made this question more challenging, more difficult than needs to be, but let's kind of clean it up and work on it together. It says here that the molar concentration of hydrogen ion is what I'm trying to find, and I'm given the density. Well, you remember density is mass divided by volume. So that if I were to take and look at what I've got here, I've got the volume, I know that, and I've got the density. Therefore, if I multiply them together, I can get the mass. 1.05 grams per cubic centimeter times 5.71 cubic centimeters, centimeters cubes cancels, tells me I'm really starting with 6 grams of acetic acid. Now we're at the similar starting point to our previous problem. Now I need to figure out what is its molar concentration. So I have to, of course, convert grams into moles and then take moles divided by my volume to get molarity. So let's do that next. I have 6 grams of acetic acid. If I took the time to calculate the molar mass of this, 1 hydrogen weighs 1, 2 carbons each weigh 12 is 24, another 3 hydrogens at 1 each, and 2 oxygens times 16. Well, that adds up to 60 grams per mole. That's the molar mass of acetic acid. So if I converted grams to moles for acetic acid, I would say every 60 grams of acetic acid is 1 mole. Grams of acetic acid will cancel, like that, leaving me with number of moles of acetic acid. Now this is the number of moles in 1 liter. If you recall, molarity is moles divided by liters, so 0.1 divided by 1, this is a 0.1 molar acetic acid solution. Okay, so I can substitute those in, molarity, moles divided by liters, and voila, I have 0.1 molar acetic acid solution. I'm going to get another sheet of paper because I ran out of space here. And we want to find the H plus concentration. In order to do that, this is a weak acid. It's not simply going to be 0.1 molar. If it were a strong acid, that would be the answer. We'd be done. But it's a weak. So look at what we've got. This is 0.1 molar acetic acid. We're trying to find the H plus, and we might think it's going to be 0.1, but that's wrong because there's a reversible reaction. So it must be a different number. It's a weak acid. Okay? So what this means is we're going to have to use a Ka value. So we look up, or we're given in the problem, the Ka value for acetic acid is 1.8 times 10 to the negative fifth under the conditions for our problem. So we can write a Ka expression for this. Ka is equal to the product concentration, H plus times acetate, products, divided by reactants. We can then substitute in the value for Ka, 1.8 times 10 to the negative fifth. We also know the initial concentration of our weak acid is 0.1 molar, and we can substitute that in at the bottom. As discussed earlier, the concentration of H plus and acetate are both unknown, but they're equal to each other because they have coefficients of 1 and 1 in front of them. So we don't know either of them, but we can substitute in x's there. And as we said, we can also substitute in our 0.1 molar for our acetic acid. Now we can solve this. 1.8 times 10 to the negative fifth times 0.1 is 1.8 times 10 to the negative sixth equals x squared. Take the square root of both sides, and x comes out to be 1.3 times 10 to the negative third molar. Well, that's the answer to the question, what is the hydrogen ion concentration? It's also the concentration of the acetate ion, although we weren't asked it. The last thing we want to do is find out the pH. Of course, pH is opposite log of H plus. I'm not putting in the 0.1 molar, but instead I'm putting in the 1.3 times 10 to the negative third molar. I type that in my calculator, opposite log of that number, and numerically I get a value of 2.9. Let's now compare the two problems that we've just done. Okay, in the first example, I started with a strong acid. It was a diprotic strong acid, and I had only a concentration of 0.01 moles. And that gave me a hydrogen ion concentration of 0.02 molarity. If I were to compare that to my weak acid, notice it's 10 times more concentrated, 0.01 moles to 0.1 moles, 10 times more concentrated, yet it gave a hydrogen ion concentration that was very small, almost 10 times less. Now, when I look at the pHs of these things, if I plug in the H plus values, my strong acid gave me a pH of 1.7, and my weak acid gave me a pH of 2.9. Now, remember this, every time you change a number by 1, that's a 10 times difference in concentration because pH is a logarithmic scale. So the strong acid, even though it's 10 times weaker, has a greater than 10 times pH. So in fact, there's a roughly 100 times difference between a strong acid and a weak acid in terms of pH in this example. It kind of reminds us why it's important to use the Ka value, unless it's okay to be off by a factor of 100 times, which I don't think it is. So the little note says, although sulfuric acid is 10 times less concentrated, based on its pH, it's basically 10 times more concentrated in terms of pH, so roughly a factor of 100 difference. I've left a few questions for you here. You can pause and try to solve these if you wish. The answers are at the bottom. Feel free to email me if you want to see if you get stuck and you can't do one of those. I'd be happy to help you with that. Finally, let's look at one last example and kind of cement this idea in our minds. So it says here, and we're working with something we've never dealt with before, cyanic acid. It says it's a weak monoprotic acid. Now, if it's monoprotic, it has how many protons? Good, 1. Do you happen to remember what the cyanide ion was? You do? Good. It's Cn1-. So the formula for cyanic acid must be HCN. So there's our cyanic acid. It's a weak acid, which means it's going to be double arrows, and it's going to produce a proton because it is an acid, and what you're going to be left with is the cyanide ion. So now we've written an expression for it. Now, the question says, if the pH of this 0.15 molar cyanic solution, so we're given the concentration of the cyanic acid is 0.15 molar. That's important to know. And we're told that it has a pH of 2.32. Well, I bet we can use the pH to get the concentration of the H3O plus. And if we know the concentration of the H3O plus, that will be the same as the cyanide. And if we know the concentrations of both products and concentrations of the reactant, we can calculate the acid dissociation constant for this problem. This is how a scientist would calculate the Ka value. They would do just what we're doing. They would make up a solution, they would allow it to reach equilibrium, check the pH, and work backwards. So let's kind of go through this together. We know that pH is opposite log of H plus, or 10 to the negative pH power is equal to the hydronium ion concentration. I'm given the pH. So if I say 10 raised to the power of negative 2.32, I will know the H3O plus concentration. I typed that in my calculator, and I got an answer of 4.8 times 10 to the negative third molarity for my hydronium ion concentration. I'm going to go ahead and put that into my equation. Now, I know that based on the coefficients, there's a 1, 1, 1. The cyanide concentration must be the same in this case. Ka is always products over reactants. So I've written my products, hydronium ion times cyanide ion, divided by the reactant, HCN. So I know the Ka value, well, that's what I'm trying to get, excuse me. I know the hydronium ion concentration. I know the hydrogen cyanide concentration, and I also know that the hydronium and cyanide are the same values. So I'm going to go ahead and put those in as the same numeric values. Now I can type this in my calculator and solve for an answer. So when I multiply that through, I get an answer of 1.54 times 10 to the negative fourth. That's how we get a value for Ka. Now, if we compare that value to something like acetic acid had a Ka value of 1.8 times 10 to the negative fifth. Which is a stronger acid, cyanic acid or acetic acid? Good. Cyanic acid is a stronger acid because 1.54 times 10 to the negative fourth is a larger number than acetic acid, 1.8 times 10 to the negative fifth. I'm sure your head's about to explode now listening to me, and I appreciate you watching all the way to the end and trying to figure out weak acids. I'm looking forward to when we can meet in person and I can answer more questions for you. I hope this video helped, and I'll see you later. All right, I'm going to say bye. I'm going to close off my little video here and stop. Take care. Bye-bye.